Good afternoon, everyone. Thank you for joining. Let's start today's session. This is we have one more extra session tomorrow, Sunday, same time, 3 to 5 p.m. If there is any doubt, you guys can go through your course and everything. And if doubt or something, you can ask tomorrow. So the new person who have joined, we have one extra session tomorrow also, 3 to 5 p.m. And there's some topic. Today we'll be mostly discussing something related to dielectric properties, and superconductivity we'll do tomorrow. And also if there is any other question, that also we can discuss tomorrow. And if there is something related to exam pattern, I'll just show you how to use the digital calculator. And then, yeah, okay, let's see. So we can start today's session now. Just let me see. I guess one, okay. Okay, so as you know, this is the session for NPTEL course Solid State Physics. Course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am PMRF TA for this course. I am from School of Physics, University of Hyderabad. And these are the recommended books for this course. Okay, so last 2 weeks, the lectures were mostly on magnetism, magnetic properties of solids, and where the professor covered origin of paramagnetism, diamagnetism, and then we saw ferromagnetism, how there are two theories for it. One was Weiss molecular field theory for ferromagnetism. Last week, the discussion was on this. Ferromagnetic materials, the to explain why some materials show ferromagnetism, there are two models. One is Weiss theory of ferromagnetism, or Weiss model, or Weiss molecular field, because this person explained, according to him, it was that there is internal field in a material because of which all the magnetic moments align together, and thus even without applying any field we have some magnetization. Okay. Even without applying any field, means the field is zero, still we see some magnetization. It was explaining some of the things that we observe, but as if we'll go as per this model and its hypothesis, the internal molecular field value was coming huge, which is not possible. Then another theory was had come up. It was given by Heisenberg, and in this, it's considered that the quantum mechanical origin, which gives a spin angular momentum of inner material, there we consider that these spins are all interacting with each other, with their immediate neighbors only, and thus they tend to be along same direction. When they tend to be along same direction, the energy of the system is lower, which we all know. Every time for any kind of system or material, the system tends to be in the lowest potential energy, lowest energy. So this is called exchange energy, or Heisenberg exchange interaction or energy, which is seen as the origin of ferromagnetism. That also depends on for some materials, the system is stabilized or has least energy when they are all parallel, the spins. Whereas for some materials, which we call antiferromagnetic materials, by this same interaction energy, Heisenberg exchange energy interactions model, mm, in those materials, the there is something, maybe it's too much detail, but there is some, this is spin of one, spin of another one, and this exchange integral, it is called the Heisenberg exchange energy equation. So this, when is positive, then the spin magnetic moments tend to be along same direction for the energy to be minimum. And when for some materials this constant is negative, then the materials, there is dot product, then the magnetic moments tend to be anti-parallel, so that overall their energy will be minimum. So the same exchange interaction energy is responsible to this behavior in ferromagnetism and antiferromagnetic material, but the change in the sign of this exchange integral when we go into equation, which I think for you people, for your stage, it's not important, but I'm just telling that same interaction energy phenomenon that we are talking about in ferromagnetic material, that same thing is responsible in antiferromagnetic materials as well, for the ordering where we see all spins are anti-parallel to each other. And what we see here, because they are anti-parallel to each other, so net magnetic moment is zero when we don't apply any field. Whereas for ferromagnetism, even when we don't apply any field, there is some net magnetic moment. So there was derivation for this that you must have very well seen in the lectures. And moving on from this, okay, there is another, yeah, then we had discussed last week just a small comparison between paramagnetic material, ferromagnetic material, antiferromagnetic material, and ferrimagnetic material. There are more categorization if we'll go in detail the types of magnetic materials. There are some materials called super paramagnetic also. So instead of going to those many, we just concentrated like the that have been mentioned in the lectures also. One is diamagnetic materials, and then we had seen derivation was also discussed, but then like we had discussed how it's mh, sorry, it goes from the origin. First, it goes from the origin because when H applied field is zero, magnetization also is zero. This is the behavior for diamagnetic material. Oops. Then we have paramagnetic materials, where we had already seen these comparisons. The susceptibility, what is the range of susceptibility, what is the range of permeability for these materials, and the mh, it's as soon as we start applying field, the net magnetic moment because I mean it's not zero anymore. Then ferromagnetic material, which have actually initially it may have something like this, but after once we have magnetized it, then even if you make the field zero, you'll get some non-zero magnetic moment. It retains the magnetic order inside it because the magnetic moments align and they want to keep them aligned together. We discussed these things, so yeah, we don't need to repeat again. And then we have antiferromagnet, where these are anti-parallel to each other. For that, MH loop is complicated, so we don't need to go into it. And then we have also said about ferrimagnetic material, which are like some aspects of ferromagnet, some aspect of antiferromagnet. How? So just quickly, like ferromagnets have all the spins parallel, antiferromagnets have magnetic moment anti-parallel and they cancel each other out. Ferrimagnetic material have opposite aligned spins, but the magnitude of spins in one direction is more and the magnitude of spins lying opposite direction is less. So overall there is net magnetic moment even when we don't apply any field. As you can see, the opposite arrow is like the spin in another direction and its magnitude is small. That we are showing by the length of the arrow. So the magnitude in opposite direction for the magnetic moment or magnetic spin is small. So there is net here, like here they were cancelling out because they were equal in magnitudes. Here they are not equal in magnitudes. So the net will be here in this direction. Same way, the net will be in this direction. So that's how these are the basic categories of magnetic materials. And the derivations were done for Landau's diamagnetic and then Pauli's paramagnetic model, and ferromagnetic we saw Weiss theory and Heisenberg exchange model. These were done with the derivations. So these were the magnetic properties part. Now in ferromagnetic also, when we were discussing, I was telling you that although we say and that MH loop for ferromagnetic material looks like this, but in the beginning it goes through this. Once when we magnetize it, then it retains its order, and it's, even if we make the field zero, it stays like this. So all this happens in ferromagnetic material, if we specifically discuss. Then what is there is another term we need to understand for this, or we can start like this, that why, like we know iron is a ferromagnetic material, and we had also seen the something called Curie temperature. It is the temperature above which ferromagnetic material loses its ferromagnetic nature and it becomes paramagnet. So for iron, the Tc is very high, like room temperature, the temperature around us at any normal time. Usually we take it as 300 Kelvin. That means like about 27 degrees centigrade. For iron, this Tc is way above 100 degrees centigrade, as much as I remember, but definitely above room temperature. So if its Tc is above room temperature, that means at room temperature, iron should be ferromagnetic. And if it's ferromagnetic, that means all its magnetic moments, magnetic dipole moments, magnetic moments are aligned. If they're aligned, then they should behave like a magnet, because they are aligned means one side, if I have some block of iron with me and all the magnetic moments are aligned like this, means one is north end, another is south end, then it should very well behave like a magnet. If I take some other some sort of what to say, another kind of iron or some other material, it should be able to attract, or something that shows me that it is ferromagnetic, because all I'm saying ferromagnetic material means all magnetic moments are aligned like this, so it should be as good as a magnetic bar, which actually we know if we have a magnet that we call, so it attracts other ferromagnetic materials usually, or some weak materials also, magnetic materials also. Bar magnet, actually we call it bar magnet. Okay, it made up of different kind of materials, may not be iron, different kind of materials anyways. So but what we see, if I'm holding iron utensil or iron block of iron also, it's not behaving like a magnetic bar. Only when I take a bar magnet near it, then we see some sort of interaction between that block of iron and the magnet, bar magnet. So when I'm bringing a bar magnet near, that means its field, the magnetic field of this bar magnet is making the magnetic moments align, and then there is attraction between them. But in itself, without the presence of bar magnet, iron doesn't, like we cannot know if it's I mean how we are claiming these moments are aligned if it's we don't see it behaving like a magnet. And the reason behind this is because of something known as magnetic domains. Either we usually call domain or specifically magnetic domains. These are kind of regions inside any magnet. When we are talking about ferromagnetic material, we don't talk about existence of domains in when we are talking about diamagnetic material or paramagnetic material. It's something talked about when we are talking about ferromagnetic material. So what happens is, if I have a material like this, if I have a material, let's say it's in this shape, and all the atoms and their magnetic moments, which I'm denoting by this arrow, all are aligned in this direction, because that's what I'm saying, that it's ferromagnet, so it should be like this. All the magnetic moments should be like this. And when it will be like this, then that means this is north pole, this is south pole. So overall the magnetic moment, I can show that this is the direction of magnetic moment in this sample, in this system. So that means one is north, another is south pole. That happens in any bar magnet, right? Even Earth has its magnetic poles and there is magnetic field around it. If this is the situation, then we know magnetic field is always is in a closed loop. So starting from emerging from north end of this system, it will be coming into the south, and then it won't end abruptly. It always forms a closed loop. Even when we are talking about a current carrying conductor, we know there is closed loop. This is magnetic field. This is what happens for magnetic field, that starting from north end, it goes like this, and at south, and inside the body it is in this direction, which I'm showing by the direction of magnetic moment. This is the direction inside. Outside, if you notice, because it's forming a closed loop, inside it's in this direction, and just near and outside, if you see, it's in opposite direction because it's taking a turn. And similarly it will be this side also, I mean, because they don't overlap, of course. And then because we have north poles here, south poles here, so there's like a region around the sample where we can feel, not we, I mean, there will be magnetic field around it if you use some magnetometer to measure. To some region, to some range around this sample, there should be magnetic field detected. Something like this, symmetric on both sides, of course. I should draw, but okay. So as you see, inside it's in this direction, but immediately outside it's in opposite direction. The field is in opposite direction. So here what happens, immediately here if you see, the field is in this direction and this direction. So the field just outside is opposing the direction of magnetic moment inside, because inside I showed you, if this is ferromagnetic material, let's say all magnetic moments should be aligned, and if they are aligned, then inside the field emanating from their position or their ordering itself is opposing them, because we said the direction in which we apply field, the magnetic moments tend to align in that direction. And here, just here near the body, if the field just outside is in opposite direction, that means it's influencing the magnetic moments here. Same thing is happening here. Here also, if you see, inside, just inside the body, magnetic moment in this direction, field is in this direction, and just outside the field is in opposite direction. So it not letting the system go to stability, it's not letting the system have less energy, because this is called demagnetizing field, because the field which is in opposite here, that is opposite direction to the direction of magnetic moment, and in a way it's trying to align it now in this direction. So initially when they all were aligned in up direction, the whole body was magnetized, but the field, because the same origin, the field which is this field loop, that is because of the alignment of these magnetic moments itself. But now they are opposing. So the same origin is opposing the cause. But anyway, not getting confused there. I hope this is clear. If there is any doubt, you can ask. So what I'm trying to say is, if we have a bar magnet, or no, sorry, I mean any kind of ferromagnetic material, a system or a bar or a sample, and all the magnetic moments are aligned, then magnetic field lines emerging out of the system will be like this, and immediately outside the sample, the direction of magnetic field will be opposite, which will be not letting the magnetic moments inside be stable because they are in opposite direction. So now they are trying it to flip. So they are called demagnetizing field, because in a way they are disturbing, demagnetizing the uh, the magnetization of this sample. Demagnetizing field they are called. And so to stabilize this, what another way can be done is, I mean, how the system turns into something where, I mean, this is ideally what we expect from a ferromagnetic material, but I'll show you this is not how it actually stays in absence of field. We are talking about, we are not applying any field. In absence of any field, how it actually stays so that its overall energy is minimum and it is stable, which every system wants to be in. So if all the moments are aligned like this, there will be high demagnetizing field. System won't be happy, in short. But what if we split this? Let's say we split into two. Some magnetic moments aligned in up direction. So overall I'm showing this one arrow to show this region has magnetic moments in up direction and this region has magnetic moments down direction. This has north here, south here, this is north here, south here. In previous direction, all the magnetic field lines always emerging from north, ending into south end. Here, magnetic field lines don't need to go like this. They can go like this, north to south, shorter closed loop, because magnetic field line of course will be making loop, but then here they can just make a loop like this. And thus, if we have a arrangement like this will be the magnetic field lines you will not get here anywhere. This is the closed loop they'll form. And here you can see that there is no demagnetizing field around here. So the instability, destability that the sample was facing here, it has reduced. Now there is some small field. Maybe the direction is still not along this, but it's smaller. Even further, it can take some arrangement by which even this small demagnetizing field or field which is still not in exact this direction can be avoided. Further, if this takes something like either like this, then north, south, south, north. So they will be forming a closed loop. The magnetic field lines will be just here. There will be no demagnetizing field now. There's no poles. I mean, all the magnetic poles are, whatever the field lines are emerging, they're all making closed loop inside itself. There is no demagnetizing field situation and no demagnetizing energy here. So if system forms its magnetic moment alignment in this kind of structure, It's called closure domain structure, and that is why we call domain. Domain is basically just a region in material. Uh, like one kind of domain has orientation of magnetic moment in one direction. If, like, say I have a material and let's just say there are three kind of domains in this. In one, there is this much region in which the magnetic moments are aligned in this direction. In another domain, the alignment is in this direction. In third one, the alignment is in this direction. So up to the region in which the all the magnetic moments are aligned in one direction, and then maybe I can just usually we just use one arrow because there are many magnetic moments. We just use one arrow to show overall this region or this domain has magnetization in this direction. This domain has magnetization in this direction. This domain has magnetization in this direction. So this region is called domain. I hope you could get. And why the domain forms is to avoid this demagnetizing energy, this demagnetizing field, which was making the system unstable if the magnetic moments will be aligned. But another thing is, when these smaller regions are formed, that these domains are formed, here you can say it was like a single domain because all the magnetic moments were aligned in same direction. So it was like one single domain. But to get rid of this demagnetizing field, it started breaking up into smaller regions, that is domains. Here we could reduce demagnetizing field, but another thing increased here, because I told you in ferromagnetic material the magnetic moments inside the material tends to align along each other. That was because of exchange energy, Heisenberg's exchange energy, which wants the system to align all the, if we are talking about ferromagnetic material, it wants all the spins to align along in one direction to reduce the system, to reduce the energy of the system. So in the beginning, when all were aligned in same direction, the exchange energy was minimum, but we had demagnetizing field which was making the system unstable. When we started breaking these alignment into these domains, the demagnetizing energy decreased, but exchange energy was increasing. Why? Because exchange energy wants the spins to be aligned, whereas we were making it not aligned. We are talking about ferromagnetic material here. So it wants all the spins to be aligned to keep the interaction energy minimum. But when we were splitting it into domains, here also, in this domain, the spin is along this direction. In this domain, they are in this direction. So the neighboring spins here are not aligned. That means exchange energy has increased. So demagnetization energy decreased, but exchange energy has increased. So ultimately, the material takes that domain arrangement in which there is intermediate we reach between some increase or decrease in exchange energy and some increase or decrease in demagnetizing energy. So there are one or two more types of energies which have their role in this, but here I just want you to keep to these two types of energies, not to make it complicated, because otherwise there is anisotropy energy also. But yeah, so the existence of domains, I wanted to tell you that even though we say ferromagnetic materials have all the moments aligned, but at room temperature that material may not show magnetic field around it because it's actually existing in a closure domain structure, something like this, just so that it can get rid of demagnetizing field. But when we try to reduce the demagnetizing energy, there is some increase in exchange energy, but it is still less than if we'll keep it like this. That will be huge destabilization and the system will not be stable. So this was why we get domains structure, and again domains are the regions in which the spin or the magnetic moments are aligned in one direction. Like this is one domain, there will be a lot of magnetic moments inside. I'm just representing this blue one as the overall what's happening here, and there will be a lot of them here also, and this blue one represents overall the direction of magnetization in this domain. Here we have two domains, here we had four domains, here we are showing we have three domains. So it depends on the material, what kind of material it is and what kind of structure it has. But overall, this is why we have these smaller regions with spins exactly not aligned, just to keep a balance between this demagnetizing energy and exchanging energy. And these I told, this is one domain, this is another domain, and the boundary shared between these different regions, these different domains, is what we call domain walls. And there's a lot that can be talked about domain walls also, but I think it's not required for this course. But I'll just tell you that domain wall, through the domain wall, if I have domain 1 here, let me go to another slide. If I have, if I'm drawing, let's say again something like this. If I have one domain where this is the direction of magnetic moment, and let's say in other direction it is like this. Let's just assume. So in the domain wall, it's not like immediately till here the magnetic moments were like this and immediately after this it's like this. This domain wall has some thickness, and inside this domain wall, like if I'll zoom this thing, then here I am calling domain 1. Here the magnetic moments are aligned like this, here they are aligned like this, and this is the domain wall region. And here if we can zoom, then we could see that the direction of these magnetic moments are changing slowly, and ultimately they are in this direction. So this domain wall is the region between which the magnetic moments go from direction of domain 1 to direction of another domain 2, I can call it. So there are different type of domain walls. 90-degree domain wall, where like this is like 90-degree, right? It is from here to going here. Somewhere we also see 180-degree domain wall, where the domain wall goes from this direction to completely 180-degree change. So the domains are changing slowly and then going this direction. So again, we don't need to go in that much detail, but yeah, I mean, there is something like this. Whenever we talk about ferromagnetism, we have domains, we have domain walls, and why domains exist? To keep the system at minimum energy, and the competition is happening between exchange energy, which wants to keep the magnetic moments aligned, and versus the demagnetizing energy, demagnetizing field, which is trying to which is actually opposing the arrangement of these spins until we reduce and make something like this closure domain structure. Okay, I hope that is clear. If it is not clear or any part you guys want to discuss again, we can. But if there is no doubt, then I think we can move on to dielectric properties and then further to doing some numerical problems. There is no question. Then let's discuss dielectric properties. So like we talked magnetic properties of material, and we talked about there's something known as magnetic dipole moment, or just magnetic moments. We represent by mu, and then when we bring magnetic field, then the materials get magnetized, magnetic moments align themselves along magnetic field. These things we were talking about when we were talking about magnetic properties of solids. Then another type of properties that solids show, not all, again, like magnetic behavior, different magnetic behavior was shown by different magnetic material. Similarly, we have property of dielectricity, where the concept is of electric dipole moment. So here we had magnetic dipole, which we usually represent like north-south pole kind of thing. Even when we are talking about a current carrying conductor, if the current is flowing say in this direction, it means it's the top is north pole. The current is flowing in this direction, means it's south pole. So this we talk about when we are talking about magnetic fields or magnetic moments. Electric dipole moment, we talk about charges, positive negative charges, and we know similar charges repel and opposite charges attract, and these charges at some small distance between them, let's say x, then they form electric dipole. Like here the north and south magnetic poles were forming magnetic dipole moment. The positive negative charges at a small distance like this, they form electric dipole moment. Yeah, electric dipole moment. This also depends what symbol we use. Usually sometimes we use mu as well for this also. And the direction for magnetic field of a magnetic moment is from north to south. Electric dipole moment, the direction is from negative charge to positive charge. This is the direction of electric dipole moment. And then there's a lot of analogies between, lot of similarity in the sense, like again, like the concept of susceptibility we had discussed here. The same thing we have when we talk about dielectric properties. Moment per unit volume. So here moment per unit volume was giving us magnetization, overall magnetization of material. Here when we talk about electric dipole moment per unit volume, we call it polarization, capital P. Usually here we were using capital M to represent the magnetization, which was magnetic moment per unit volume. We denote it using capital P. Polarization, which is dipole moment per unit volume. And so susceptibility here, like here it was M over H. Here it's the polarization we get when we apply electric field. Basically this is it, and then depending on we are using CGS unit or SI unit, which is MKS, meter kg and second thing, then for that direction there's sometimes this permittivity of free space constant comes, but overall it's the relation between we apply electric field and then these electric dipoles interact with that electric field, like we were seeing when we were applying magnetic field H, and then the system was getting magnetized because the magnetic moments were interacting with the field and getting aligned along or opposite. In the same way, when we apply electric field, like in magnetism we were talking about MH loops or MH graphs. In dielectric properties we have PE graphs. We are applying electric field and we get polarization in the materials. That is electric dipoles either aligning themselves or something else, doing something else. Especially for like here we had ferromagnetic material, and I told you we get we had talked about last week, I think we have hysteresis loop, right? Because unlike when we were talking about para, yeah, or diamagnetic material, as long as we apply some field, there is some magnetization. But for ferromagnetic material, once we magnetize it, after that, even if I make the field zero, there is magnetic moment. That is the magnetic moments are aligned. The same way, dielectric materials, we have ferroelectric materials in which we get hysteresis loop. That is, once I apply electric field and all the electric dipoles in that material are have aligned in one direction, then even if I remove the electric field or reduce the electric field to zero, right, here you can see electric field value is zero, but still there is some polarization. So the similar behavior of things that we were seeing in magnetization or magnetic properties of material, the same things we see. So many things are very similar, whatever origin we were seeing there and here. I mean, in analogy, we can understand a lot of things in dielectric properties also. Like another thing here, when we apply H, there is magnetic field induced magnetic flux density, or there are many terms we had discussed in what is the subtle difference, and then still, like I told you, there's interchangeably they are still used. That's okay. Similar way, when we apply electric field, we say electric field, like here electric field induction was happening. Here we represent using capital D. Electric displacement, it's called. And the relation is electric permittivity thing. This was it. And then there was one derivation, I think that in this week's lecture related to this. It's known as Clausius-Mossotti relation. The relation itself is this. There is whole derivation. This is R. You can find it very well explained in the lecture. And so this relation is, it tells us, it's actually connecting the whatever material we are talking about. So it's dielectric constant. This is permittivity, relative permittivity. Like we had permeability, how easily the material can get, how easily it can be magnetized. The same way we have these, how easily they can be, let's say, polarized. And so this is called relative permittivity constant. These things actually we have learned in school, but not. These also, it's called dielectric constant. And that's how the name dielectric properties comes. And this relation tells us how a material's dielectric constant and its polarizability, that how easily it can be polarized, that material. So that material, how easily it can be polarized, and the value of its dielectric constant, this relation connects that. This is polarizability and these are dielectric constant. So it connects, this relation connects these things. And it also, if we go, because dielectric constant then connects further to optical properties of material. And so it also, this equation also is helpful when somebody wants to understand optical property of medium, because in optical medium we use light, and light we know is electromagnetic in nature. So it has electric field component and magnetic field component. So the similar way, like electric field, how the atoms dipoles are interacting in the presence of, or behaving in the presence of, electric field. So there also this relation is useful. The derivation you can see in the lecture. And I think there was not much, only one class of, yeah, apart from derivation, there was not being discussed in, maybe it's not in detail for you guys. So we also should not go in much detail. But apart from this, in very short, the origin of dipole moment was discussed. Where we had seen basically three types of dipole moments are there in any material. Any kind of dielectric material that we are calling, it may have all these three types of dipole moments. Like if you remember in magnetic material, when we are talking about, we discussed that every material has diamagnetism in it, because the origin of diamagnetism was the orbital angular momentum of electron, right, in atom. Only thing is, if a magnetic material has some other magnetic property also, then diamagnetism gets suppressed. Like if it has magnetic ordering, if it's ferromagnetic, then the diamagnetism is very small in magnitude, so its influence won't be seen. So similar way, when we are talking about dielectric materials, there are different type of origin of dipole, electric dipole moment. Some materials may have all, some materials may not have one or other. And these different type of dipole moments are, one could be electronic dipole moment or electronic polarizability. This is an atom, okay? An atom, we know at the center we have positive charge, and around it is moving our electrons. So it's like a cloud of negative charge around the center, which is positive. So because the positive is at the center, and this whole cloud of, because electrons are around everywhere here, depending on what is the atomic number of this atom. If the center of this negative charge, we'll see that will also be at this, almost at the same, where the positive charge center is there. So overall, it's like charge neutral. It's charge neutral until it becomes some ion. Anyways, so this is how an atom is usually. But if we apply electric field to it, then we know uh, the force of electric field, the present, because of presence of electric field, the force that a charge experiences is given by this, and the direction also, and the positive charge will go in the direction of electric field, whereas for negative charge the direction will be opposite. That means if I am keeping this neutral atom in the presence of electric field, then positive charge will drift, not huge, it's very small, but it's still very significant. The displacement right now, the positive charge, and I said this negative charge cloud also, if we'll see its center, it will be at the same place. But when in the presence of electric field, there will be small shift. Let's assume if the center is still here, and because the mass of neutron is 1,000 times more than mass of electron, so even if I assume that mass of the positive charge is still at the same place, the negative electron cloud will shift little bit, such that overall maybe I can say the negative charge center has shifted now. It won't be completely like now nucleus is here and all electron cloud center has completely gone out. It's not huge, but it's such, like something like this, that the center of that negative cloud is not coinciding with the positive center anymore. And this displacement x is what is giving us electric dipole now. So this is electronic polarizability or electronic dipole moment origin. Okay. Another is ionic polarizability. When we have ionic molecules like NaCl, we know Na plus is the positive ion, Cl minus is negative ion, and when they are molecule like this, they are still, their positive negative charges center are coinciding, until we apply electric field, which leads to small shifting between the positive and negative centers, and thus again there is some displacement between the positive and negative charge, and that gives us the charge and the displacement. This gives us electric dipole moment. So this happens for ionic molecules. Third is orientational polarizability, which already have some orientation. Like for electronic polarizability, ionic polarizability, we talked that in the beginning they are charge neutral. Okay. And after applying electric field, there was some shifting between the positive and negative charge position. Even for ionic, the same. But orientational dipole moment, also called polarizability, are molecules which, third was orientational or dipolar polarizability. They are already like we were talking about permanent magnetic moments. I mean magnetic moments like ferromagnet, which already have magnetic moments even in absence of field. The same way, these type of dipole moments, where even in absence of any electric field, even when we are not applying an electric field, still there is net electric dipole moment, because this is how they, even without any application of electric field, this is how they are existing. Like H2O, a very common example, O1H, and the direction is from negative to positive. Overall, it will be like this. So they exist as these electric dipoles. And then further, if you apply electric field, then these moments will interact with the electric field and accordingly they will align. But even in absence of field, they have electric dipole moment. These were the things discussed in this week's lecture. Then I think there was something about little bit about capacitance, and that how whenever we have, if two charge plates and we connect them to a voltage source, then one plate will get all the positive charges, another end of this plate will get all negative charges, and there will be this positive negative voltage which lead to electric field between them, and then it's basically like a capacitor. And that is what happens any dielectric material. That means, okay, what material we are calling dielectric is when there is no flow of electric current. Electrons are not able to flow. Usually the poor electrical conductors of the materials which are poor electrical conductors are what we call dielectric materials. So these materials, if you apply voltage, the current is not flowing there because their resistivity is very high. There, the charge accumulation at one end will happen, and then this they get behave like capacitors. Okay, so I think we can move on to doing some questions related to this. Mostly this on superconductivity. If there is something we can discuss in tomorrow, we have the extra session as I said in the beginning. Yeah, I think we can move on to questions. Okay. So the first question is, two parallel conducting plates are separated by 5 millimeter we have two parallel conducting plates. These are two plates They are kept parallel, separated by a distance of 5 millimeter, and space between them is filled with a dielectric of dielectric constant 3. So it's like a capacitor, but here in between them it's not air, but it's filled with some kind of material for which dielectric constant is 3. The electric field intensity in the dielectric is the electric field intensity in the dielectric is 10 to the power 6. 10 to the power 6 volts per meter. Calculate the polarization in the dielectric material. We know, so electric field in the dielectric will be E naught is the applied field. Okay, E naught will be the applied field, and inside the material what will it be? It's like the same situation we were talking about in magnetism. Just for analogy, when we apply H, the material based on its permeability, it gets magnetic flux density B. Same way here, we are applying 10 to the power 6 volts per meter electric field. But what this is a material with some permittivity of permittivity constant. So electric field inside that, these are the plates inside some material I have kept. Okay, for this material we are talking about, the electric field inside will be given by this relation, where E naught is the field I am applying, and I want to find out the electric field induced in this material, this dielectric material. That will be E naught this was the electric field intensity in the dielectric. That means this was what was inside the material. Okay, sorry. And E naught is what we are applying. So E we already know, which is inside electric field intensity inside the dielectric. That means E naught, which we want to find out, the one that we are applying, it will be E times epsilon r. And E we know that the electric field induced inside the material is 10 to the power 6, and this dielectric constant is 3. So the electric field, when I'm using field word here, it's electric field. So the electric field that was applied actually was 3 times 10 to the power 6 volts per meter. And what was induced inside the dielectric material was 10 to the power 6 volt per meter. Again, depending on what was its permittivity. So this is the field that was applied. Now we have to calculate the polarization in this dielectric material. So polarization will be epsilon naught, epsilon r minus 1 E naught. The field that we applied, dielectric constant or relative permittivity, and this is permittivity of free space. So it's a constant permittivity of free space, and the value is 8.854 times 10 to the power minus 12 farad per meter. This is its unit. Putting these values, 8.854 times 10 to the power minus 12. This farad per meter is SI unit. And then dielectric constant was 3 minus 1, and E naught was 3 times 10 to the power 6 volts per meter. So when we will calculate this, I'll be using my calculator. 8.854 times 2 times 3 means 53.124, and now the powers 10 to the power minus 12 and 10 to the power 6, this will be 53.124 6 minus 12 means 10 to the power minus 6 coulomb per meter square. Meter square. So the correct answer will be this. Okay, because all the answers have magnitude with decimal after first digit, so we'll do that here also. 5.3124 times 10 to the power minus 5 coulomb. Sometimes we only use this capital C also. Coulomb per meter square. 5.3124. So this is the correct answer, option C. Next question is, these values of some constants, again I'm saying you need to remember, because if it's not given in question, like here this, then you should better remember. Polarizability of argon, there is gas, it's noble gas. Polarizability of argon is this. Calculate dielectric constant of argon at NTP. This is normal temperature pressure. This is what it means. NTP, normal temperature pressure. Pressure, I think, is 1 atmosphere when we say normal NTP, and temperature, I think it usually means room temperature, that is 300 Kelvin, just to make you clear what NTP means. Okay, so polarizability is given, we need to calculate dielectric constant. Polarization is number of electric dipoles, polarizability, and electric field. This is one relation between electric field and polarization. Polarization also can be written as, these all different formulas you will see when you will go through the equations in this week's lecture. Okay. So all these are correct and they are different types of relation. Okay. So next is this relation that we used just in previous question as well. And N, as I said, is the number of electric dipole moments. Alpha is atomic polarizability, E is the electric field when interaction between dipoles is there. From equation 1 and 2, we can simply equate these two things, and then it will be like this. Epsilon naught, epsilon r minus 1 and E. Yeah, here E will be cancelled and we will be left with N alpha. Now this N is number of atoms per unit volume, and number of atoms at NTP means 1 mole, which has 6.023 times 10 to the power 23 atoms per mole. And volume is at this pressure is this 22.4 mmHg means 10 to the power minus 3 per meter cube will be number of atoms per unit volume, and we'll calculate this. 6.023 divided by 22.4 will be 0.2689. These powers 10 to the power 26 per meter cube, or 2.689 times 10 to the power 25 per meter cube. This is number of atoms per unit volume. Now putting this N here, I will be able to calculate this polarizability we know, N we have calculated. We'll be able to calculate epsilon naught, we know it's a constant, the value we know. Epsilon r we'll be able to calculate. So let's do this. So epsilon naught n times alpha was epsilon naught epsilon r minus 1, and e both sides it was cancelled. So epsilon r minus 1 will be epsilon naught divided by n times alpha. Let's do this. Epsilon naught, the value is 8.854. 8.854 times 10 to the power minus 12. N that we just found out, say 2.689. 2.689 times 10 to the power 25. And alpha is given 1.8 times 10 to the power minus 40. 0.8 times 10 to the power minus 40. Oh, I did a mistake, sorry. Epsilon r minus 1 means this will be n alpha divided by epsilon naught. I'm keeping it here and I'm sending it opposite side, so I'm sorry. This will be 2.689 times 10 to the power 25 times 1.8 times 10 to the power minus 40 divided by 8.854 times 10 to the power minus 12. Okay, now it's correct. And then if I bring this minus 1 on another side, then this will be my answer. When we do this calculation, 2.689 times 1.8 divided by 8.854, this will be 0.5467, and the powers 10 to the power 25 minus 40 plus 12, and then I have plus 1 here. This will be 25 minus 40 plus 12 minus 3. That means 0.5467 times 10 to the power minus 3 plus 1. That means this will be 1.000547. So the correct answer is the closest that I can see here, 1.00054. This is the closest we can get. Our answer is different here, but almost matching option C. Sometime what happens is they have not given the value of this permittivity, right? And sometimes the answers to the last position may differ depending on how many digits I'm taking for this constant, this 8.854. If we don't take this 4, maybe there is some change in this last digit. So that's how sometimes that's why it's important, if they have mentioned the value of the constant, then it's better to use that value to whatever. If they are only using it to 2 decimal digit or even 1 decimal digit, better to use that. But here in this question they did not give, so it's okay what we have used. So finally what we'll see, to whichever our answer matches the best. So that is the option C for this question. So that is what we'll answer. Okay, next question number 3. Estimate the shift of electron cloud with respect to nucleus in argon atom when field of 10 to the power 5 volt per meter is applied. Polarizability of argon is 1.8 times 10 to the power minus 40 farad meter square. Okay, so in case of electronic polarizability, the polarizability is given by the number of the atomic number, that means the number of, because atomic number tells us how many electrons will be in that atom. So Z times E, the charge of electron, and then displacement between the positive negative charge, divided by the electric field. This gives us the electronic polarizability. Okay. And D is the separation between, as I said, positive negative charge. Here we are already given polarizability, we are already given electric field. For argon atom, we know atomic number, we know which is, for argon atom, atomic number is 18. We know the charge of electron, which is 1.6 times 10 to the power minus 19 coulomb. Thus, we can find out D. It is the, we have to estimate the shift, right? The shift between positive and negative charge. So D is what we need to find out. So rearranging here we will get D is E times alpha divided by Z times E. Electric field values now we'll put 10 to the power 5. Just keep in mind everything is an SI unit. 10 to the power 5. Polarizability 1.8 times 10 to the power minus 40. Atomic number 18. Charge of electron 1.6 times 10 to the power minus 19 coulomb. Now when we will calculate this, 1.8 1.6, this will be 0.0625, just the magnitudes. Now when I will consider the powers, 10 to the power 5 minus 40, and this will be plus 19. So it will be 5 minus 40 plus 19. That means 10 to the power minus 16. So the answer is 0.0625. 0625 times 10 to the power minus 16 meter will be the distance between the, the displacement between the positive negative charge for this argon atom. Our answers are in this way. It is, I need to shift this decimal point. When I will shift it, it will be 6.25 times 10 to the power minus 18 meters. And the option that matches the best is option C. 6.25 times 10 to the power minus 18 meters. Question number 4. Ammonium chloride gas has dielectric constant given at 0 degree centigrade, and dielectric constant is this at 100 degree centigrade. Number of molecules per unit volume, capital N, is this at 0 degree centigrade. Since we know 1 degree centigrade is, when we convert from degree centigrade to Kelvin, 0 degree centigrade means 273 Kelvin, right? So we'll convert all these, either we can convert into Kelvin, that would be better actually. So anyway, so this is the question. We have to calculate the permanent dipole moment for this ammonium chloride, NH4Cl, anyway, whatever is the formula, and this is ionic molecule, and we have to find out permanent dipole moment of ammonium chloride. So the total polarization for a material, from all the different origins of moment, the total polarization can be written like this. This is the number of molecules per unit volume. This we discussed, there are 3 origins: electronic polarizability, ionic polarizability, and then we had dipolar or orientational polarizability, and then the electric field that we are applying. Here N is the number of molecules per unit volume, E is the electric field that we are applying, and as I said, this is electronic polarizability, ionic polarizability, this is permanent dipole moment. Okay, so considering these both, let's just call it this polarizability. Then I can just shorten this to this thing. Electric field. Now also we know the relation between another relation between polarization and electric field in terms of dielectric constant. Polarization in terms of dielectric constant, this is another relation. Now using this equation and this equation, when we equate the right hand sides, will be epsilon naught, epsilon r minus 1, and electric field we can just remove, it's common on both sides. It will be n alpha naught plus qdt epsilon r minus 1 Now we had two cases here. This we just found out the relation in terms of dielectric constant and this. Now we were given two cases. One at 0 degree centigrade, that is 273 Kelvin, dielectric constant value is this, and at 100 degree centigrade. And as I told every time, it's better to convert the temperatures in Kelvin, because otherwise if you'll put 0 in your calculation, it will be very different. But that's why it's better to keep it in Kelvin. And 100 degree centigrade means 373 Kelvin. Usually it goes 273.15, but I think just keeping it to this is also okay. So the next is at 373 Kelvin, the dielectric constant is this value. So using these two situations, situation 1, now I put those values here. That is the dielectric constant at 273 Kelvin. What is the value? Dielectric constant at 273 Kelvin is 1.0083. 1.0083 minus 1 is equal to n divided by epsilon naught alpha naught, or I can just multiply also, but okay. This right now is still 3 kb and T is 273 Kelvin. This is first. Second case, at 100 degree centigrade, dielectric constant is 1.0049. 1.0049 and by epsilon naught alpha naught plus P square divided by 3 kb 373. Now using these two relation to eliminate the unknown, and then to be able to find out, like here the alpha naught was unknown, and then so that we can, this we know, so that we can find out the dipole moment value out of this. So one thing what we can do is we can subtract equation 2 from equation 1. Minus 1 is here, so that we can get rid of this alpha naught. Okay. Equation 1 minus equation 2, we'll get 1.0083 minus 1.0049, and I'll multiply all this. So n alpha naught by epsilon naught, n alpha naught by epsilon naught will be cancelled, and I'll be left with this multiplied by this minus this multiplied by this. So it will be n mu p square divided by 3 kb, and here I have 1 over 273 minus 1 over 373 from here, right?
this, subtracting this, 1.0083 minus 1.0049 is 3.4 times 10 to the power minus 3. And this n is given to be 2.7 times 10 to the power 25. So I'll put the value 2.7 times 10 to the power 25. This dipole moment we need to find out. 3 kb, value of kb is 1.38 times 10 to the power minus 23. And we'll calculate this. I missed something. I think there is epsilon naught also in the denominator. I missed that. So in denominator I have epsilon naught also, whose value is 8.85 times 10 to the power minus 12. And then here I have 1 over 273. If I just do this calculation, 1 divided by 273 minus 1 divided by 373. Answer is 9.82 times 10 to the power minus 4. Okay, so this will be, okay, let me just take care of right hand side. So this will be 2.7 times 9.82 divided by 3 divided by 9.38. Okay. This will be 0.723655, and the powers 10 to the power 25, and here 10 to the power minus 23, which will become plus 23, this will become plus 12, this will be minus 4, and then I have this dipole moment square, and here of course 3.4 times 10 to the power minus 3. So the value of this, when I want to find out, that means this will be in numerator and this all will be in denominator, 0.723655, and this power will be, let me see, 25 plus 23 plus 12 minus 4, 10 to the power somewhere. Oh, 10 to the power 25 So it will be 10 to the power minus 10 to the power 56. And then when I calculate this, it will be 3.4 divided by 0.723655. This will be, I'll write here, oh sorry, I don't have. This mu square becomes 4.6984, 4.6984, 10 to the power minus 3 minus 10 to the power minus 56. 10 to the power minus 3 minus 56. 25 plus 23 plus 12 minus 4. Yeah, it was 56. Okay, so minus 3 minus 56. I can write it like 4.6984 times 10 to the power minus 59. This is in square. Now I need to find out this. That means root of all this. And that will give me 6.85 times 10 to the power minus 30 coulomb meter. Okay, if we shift power, it will be minus 60, so it will become 30, and root of square root of this will be this. So this is the dipole moment, 6.85. Option C is the correct answer. Question number 5. A sealed off vessel with 2 electrodes to measure the dielectric constant of a gas has a pressure of 760 mm of Hg. So pressure has also very different units. Usually when we say pressure is like force per unit area, then sometimes we also say its unit is Newton per meter square, because force per unit area. But otherwise, when we go for measurement of pressure, atmospheric pressure or any kind of pressure, we use very different types of units: Pascal, bar, torr. Then this mm of Hg, it's a device that has mercury in it, Hg, that's why Hg is the symbol of for mercury, right? So that this is a device has a U like tube, and there's this mercury is filled inside, and depending on how much is the displacement in that, something is like this, and it is mercury filled, and then depending on how much displacement, like one side will be up, one side will be down, depending on how much is the displacement on the up and side, it depends on the pressure at that place. So this is how we tell what is the pressure. This is also one way. That's why sometimes the unit of pressure, when we express, it is like some 760 millimeter of mercury. That is, this is the difference, 760 of Hg. So this is also one unit of expressing pressure. So we'll see, we'll need to convert it into something that is useful for us. But okay, so for time being, the pressure is given 760 of Hg, of mercury at 300 Kelvin. We have to find out the electronic polarizability. Okay, and this pressure is given. Okay, so this is for a gas. Okay, and for real gas, we know for ideal gas, we have ideal gas equation, which is PV is equal to NKBT. This is ideal gas equation. I mean, equation for ideal gas. That's why it's called ideal gas equation. Here, N by V, number of atoms per unit volume, if I do, then this will be P divided by KBT. Okay, and this is number of molecules per unit volume. That means this is also number of molecules per unit volume. And here number of atoms is not given, volume is also not given, but pressure is given, Kv is a constant, and temperature is given. So to find out electronic polarizability, I need number of atoms per unit volume, and since number of atoms per unit volume is also equal to this, and these things I know, so I can calculate. So to calculate this, as I said, first we need to convert this pressure to something useful for us. So this 760 of Hg, as I said, it's unit of pressure. 1 of Hg is equal to 133.322 Pascal. Pascal is also one unit. And why I told there are many, 1 bar, 1 torr, Pascal, because this, when we put it in Pascal, this Pascal
1 Pascal is equal to 1 joule per meter cube. Because joule also, if you'll see, joule is like work done. It's unit of work done also, and work done, if I'll convert in this, will be Newton meter, because force and displacement is the work done divided by meter cube. So this will become Newton per meter square, which is again unit of pressure. So all this is correct, but when I'll convert this like this, I'll be able to put it into joule per meter cube. 1 mm of Hg is 133.3 Pascal. So this pressure, which is given to be 760 mm of Hg in Pascal, when I'll convert, I'll multiply it with 133.322, and then kb, Boltzmann constant, I know the value, 1.38 times 10 to the power minus 23, and then temperature is 300 Kelvin. So this number of atoms per or molecules of this gas, number of molecules per unit volume will be, let's calculate this, 760 times 133.322 divided by 1.38 by 300. This will be 244 times 10 to the power 23 per meter cube, molecules per meter cube. This is number of atoms per unit volume. Now, susceptibility, dielectric susceptibility is equal to this number of atoms per unit molecule and polarizability divided by permittivity of free space. And this chi susceptibility is equal to this. So this is my equation. Polarizability I need to find out. N I have, this is a constant, this dielectric constant. This is this, and okay, so from this relation, what will be the value of alpha? Alpha will be epsilon naught, epsilon r minus 1. This we have used earlier also, this relation. That's okay. This divided by number of molecules per unit volume. Now this dielectric constant of gas is 715. So alpha will be 8.85 times 10 to the power minus 12 times 1.006715 minus 1. In denominator we have this n that we calculated, 244 times 10 to the power 23. 244 times 10 to the power 23 per meter cube. So when we will calculate all this, alpha will be 2.43 times 10 to the power minus 39 farad meter square. So option A is the correct answer. Question number 6. Benzene has a static dielectric constant 2.28 at 300 Kelvin. Calculate the polarization when the plates of parallel plate capacitor are immersed into benzene. So we have a capacitor which is being immersed in benzene, means earlier there was air between it, now there will be benzene between it. This is capacitor. and all this is at room temperature. Electric field of 300 is applied across the plate. This is 300 volt per centimeter. Keep in mind this is not SI unit. We should better change it. Consider there is no ionic bonding or permanent dipole. So only electronic polarizability is there. And we have to find out polarization here. Okay. Now polarization and electric field, the relation we know. This is one relation. Epsilon R is given. Electric field value is given. Let's convert it into volt per meter. It will be 300 volt, and centimeter to meter is 10 to the power minus 2 meter. Yeah. That means this will be 300 times 10 to the power 2 volt per meter. Yeah, that's okay. So polarization will be epsilon naught value 8.85 times 10 to the power minus 12. Dielectric constant value is given to be 2.28. This one. E is 300 times 10 to the power 2 volt per meter. Calculating all this. 8.85 times 300 times 1.28 is 3398.4, 3398.4, and the powers 10 to the power minus 12 plus 2, that means 10 to the power minus 10. And moving the decimal digit, 3.398 times this will be 10 to the power minus 10, and if I move it 3 points, that means 10 to the power minus 7 coulomb per meter square. Hence option A is the correct answer. Question number 7. Calculate the separation between positive and negative charges of helium atom when helium gas is placed in electric field. Polarizability of helium is this. Consider there is no ionic bonding, no permanent dipole, means only electronic polarizability is to be considered. Again, polarization is number of atoms or molecules, number of electric dipoles, and the dipole moment. And so we can write it like this. Dipole moment is polarizability times electric field. So from this we have this relation. It is mu is equal to dipole moment. This is pretty straightforward also. So alpha polarizability is 0.18 times 10 to the power minus 40. Electric field is 6 times 10 to the power 5 volt per meter. So now I need to convert. Then we will calculate. This will be 0.18 times 6. That means 1.08, and the power 5 minus 40, 10 to the power minus 35 coulomb meter. So this is dipole moment. We need to calculate separation between charges. So we know dipole moment is the charge and the separation. So total dipole moment value we have calculated. Charge will be what? Charge of one electron times atomic number. Because it's helium, so helium's atomic number is 2. So this will be 2e, and the separation we need to find out, and value of, okay, let's rewrite it first. We need to find out d, so it will be mu over 2e. And dipole moment is 1.08 times 10 to the power minus 35. 1.08 10 to the power minus 35 divided by 2 times E is 1.6 times 10 to the power minus 19 coulomb.
1.08 divided by 2 divided by 1.6, 0.3375, and the powers minus 35 plus 19, that will be 10 to the power minus 16 meter. And shifting the decimal, 3.375 times 10 to the power minus 17 meters. 3.375 times 10 to the minus 17 meter. Option A is the correct answer. Question number A. There are 10 to the power 27 HCl molecules per meter cube in HCl vapor. Determine orientational polarization, which we know is permanent dipole moment, at room temperature, that is 300 Kelvin, if vapor is subjected to an electric field of 10 to the power 6 volt per meter. Permanent dipole moment of HCl dipole is this. Ignore ionic and electronic polarizability. Okay, so as we were discussing that a material can have all these three type of polarizability or one of these, or I mean one or two, whatever. So here it has orientational or dipolar moment, and we have to ignore ionic and electronic polarizability. Okay, so dipole moment of HCl is 1.04 dBi, and it's given 1 dBi means this coulomb meter. So means 1.04 dBi means 1.04 times 3.33 times 10 to the power minus 30 coulomb meter. This is the dipole moment, and then we dipole moment times electric field, and we'll calculate 1.04 times 3.33 times 10 to the power minus 30, and electric field is 10 to the power 6 volt per meter, and kBt, we need these things. kBt will be 1.38 times 10 to the power minus 23, and temperature, temperature is 300 Kelvin, 300. When we'll calculate this thing, this will be 3.4632 times 10, this will be 3.4632 times 10 to the power minus 24 joules, whereas this kV times T, this will be 4.14 times 10 to the power minus 21 joule. So this is 10 to the power 10 to the power minus 21, this is 10 to the power minus 24, that means it's very 1000 times smaller than kBt. Here this is 1000 times smaller than kBt. So under this condition, orientational polarization will be given by this formula, and we substitute these values. The number of atoms per unit volume is given to be 10 to the power 27, and magnetic moment 1.04 dBi, and when I can convert it to coulomb meter, it will be this. Then I have to take square of it and multiply it by electric field, which is 10 to the power 6, and then in denominator we have 3 kBt, means 3 times 1.38 times 10 to the power minus 23, and the temperature is 300. Then we calculate all this. 1.04 times 0.04 times 3 divided by 3 divided by 1.38, 300. It will be 9.6568, and the powers, so 10 to the 27, and here I'll get 10 to the power minus 60 plus 6 plus 23, 9.6568, 10 to the power 27 minus 60 plus 6 plus 23, 10 to the power minus 4 coulomb per meter square. In a way, did we make some mistake or something? This is 27. We can divide this again. This is 1.04 times 3.33. Okay, divided by 3. Divided by 1.38. Divided by 300. 9.65. Maybe I missed this or something. So now I'm getting 9.6568. Maybe I forgot to write this. I'm getting 10 to the power minus 3 here also, and then all these powers. So in total there is minus 3 also. 9.6568 times 10 to the power minus 7 coulomb per meter square. Option A is the correct answer. So these were the questions that we had for this week's session. These are all based on dielectric properties concept that was discussed this week, and I hope all the things are clear. And tomorrow, one more extra session we'll focus on superconductivity, and then few things if there is something related to exam pattern or something. I'm not very clear about it, but at least I'll show you the digital calculator, how it's usually different than the one we use, the physical calculator. And still, if there is some kind of doubt, you can ask. And I think we can end today's session. Question? Let's see this one. Let's stop the recording now.